Hi everyone, my name is Guillaume.
And mine is François.
And today we wanted to talk about cats and mice.
But why cats and mice? Is it because they are so cute?
No, it's because of the Numberphile video linked below.
Ah, fine. But what is that video about anyway?
Oh, it's simple. There is a mouse in a circular pond that wants to go out of the pond. But a hungry cat turns around the pond and tries to catch the mouse. How can the mouse escape, knowing that it swims more slowly than the cat can run? Once on the ground though, the mouse is much faster. But it first needs to reach the edge safely.
That sounds like an interesting problem. Well, if you want to compare a lot of different solutions for this problem, you can find them in the video linked below. But here, we are gonna find the best solution.
And we will see that it's better than everything they proposed. They divided the problem into two parts and we will see how to improve both of them.
So, we have this mouse in a circular pond. To start with, I think the mouse wants two things. It wants the cat to be on the opposite side of the pond, and it wants to be as close as possible from the edge. This will maximize the distance the cat needs to cover, while minimizing the distance the mouse has to cover.
But how do you achieve that? Let's introduce the concept of angular speed. The cat can do a certain number of complete turns per minute. We can calculate this by dividing the perimeter of the circle by the speed of the cat. The mouse, when it's close to the center, moves on circles of much smaller perimeter. Therefore, even if slower, it can do more turns per minute.
Here is an animation showing this.
In this animation, there are 3 mice swimming in circle at the same speed. And we can see that the one closer to the center ends up opposite to the cat more quickly.
Okay, so there are some radiuses at which you can end up opposite to the cat if you run in circle. But what is the maximum radius at which you can manage that? I guess it depends on how much slower the mouse swims compared to the cat.
Yes, indeed. 3 times more slowly and your maximum radius is 1/3 of the full radius. And if you go 5 times more slowly, then it's 1/5 of the full radius. Why? Because the perimeter is proportional to the radius. So the distance to cover is 5 times smaller if you are 5 times closer to the center.
Looking at the animation, I can see a problem though. When you are close to the limit radius, it seems like it will take you forever to outrun the cat. So it doesn't seem very practical. Let's make a graph showing the time it takes to be opposite to the cat in function of the radius at which you swim.
Indeed, there is a problem. We see that as we begin closer to the limit radius, it takes more and more time to end up opposite to the cat. At the limit radius, you will never manage to outrun the cat.
There must certainly exist a better way to achieve this than swimming around in circles. A solution for which you don't need to swim for so long before being opposite to the cat. Well, we can see that in the center, it's super easy to end up opposite to the cat. But then you are very far away from the edge, so I guess it's not super useful either.
I have an idea. Instead of trying to outrun the cat, maybe we can try to start from the center and gradually reach the limit circle while always staying opposite to the cat.
Oh, smart! So that means that the mouse should always have the same angular speed as the cat.
That sounds easy to write down as an equation. Let's do it. The mouse turns at the same angular speed as the cat. The angular speed of the cat is Vc divided by the full radius of the circle. And to make things simpler, we can decide that the radius of the pond is 1. We can do this without loss of any generality. Therefore, the angular position of the mouse is Vc times t.
To describe the trajectory of the mouse in polar coordinates, we need two things: the angular position and the radius of the mouse in function of the time. We already have the angular position, so we will now try to express the radius in function of the time.
How much the mouse progresses towards the edge depends on the direction in which it swims. The mouse has to choose its direction to divide its speed between swimming towards the edge and turning around in circle.
Let's make a drawing of what happens when the mouse swims over a small duration of time dt.
The speed of the mouse Vm is always the same, but it has a direction alpha.
If alpha is close to 0, the mouse goes quickly towards the edge, but it's not turning around in circle. On the contrary, if alpha is close to 90 degrees, then the mouse moves very quickly along the circle, but it doesn't move towards the edge. So, I guess we have to pick a value of alpha between those two to respect the constraints.
Let's zoom on the triangle defining the relationship between the speed of the mouse, its radial speed, and its angular speed.
In this diagram, Vm is the speed of the mouse.
V theta is the mouse's angular speed, which is the speed at which the mouse turns around the center in circle. So, V theta is equal to d theta over dt.
And Vr is the mouse radial speed, which is the speed at which the mouse moves towards the edge. So Vr is equal to dr over dt.
The radial speed of the mouse is the projection of its speed on the radius, and this is equal to Vm cosine alpha.
From there, we get the differential equation for r, which is dr over dt is equal to Vm cosine alpha.
But this expression depends on alpha, which we have not yet expressed. Let's use the angular speed to do so.
The angular speed is the speed in the perpendicular direction divided by the radius. So the angular speed of the mouse is Vm sine alpha divided by r.
To maintain the cat opposite to the mouse, the angular speed of the cat and the mouse should be the same.
For the cat, the angular speed is Vc divided by the full radius of the circle, which we already defined as 1.
And the angular speed of the mouse and the cat are the same only if Vm sine alpha over r is equal to Vc. And from this, we can derive alpha.
Cool! We now have two equations with two unknown functions, r of t and alpha of t. Let's see how we can solve that system.
First, let's isolate sine alpha, and then let's take an arcsine on both sides. We have then alpha is equal to arcsine of Vc over Vm times r. Second, let's place alpha in the other equation, so we have one equation containing only the unknown r.
Now, we can solve this equation to find r in function of t. It looks kinda difficult to solve because you have the derivative of a function depending on the function itself. Luckily, if you look closely, it looks very similar to the derivative of the sine function. And if you pick the good constants, you find easily that r of t is equal to Vm over Vc multiplied by sine of Vct.
Okay, now that we have both r of t and theta of t, let's draw it. I wonder what it looks like.
Wait, but it looks like a circle!
Let's superimpose a circle on it to check if that's really true. Yes, it's a circle.
Amazing! And it's not even a circle, it's half a circle. Such a small distance to swim compared to the infinite distance you had to swim based on the Numberphile solution.
So clearly, our mouse is smarter. In only a few seconds, it reaches the limit circle opposite to the cat.
Great! So now we are ready to tackle the second part of the problem. Alright, we are now opposite to the cat. That sounds cool, but what do you do from there?
You go straight to the edge following the shortest path.
Well, that's the solution that Numberphile proposed.
But is it the best one?
Are you not convinced?
Not yet.
Okay, let's see if at least it is the best straight line.
Hint, it is not.
Let's recall that the pond is of radius 1. We have a mouse swimming at speed vm. Picking up from where we ended up after the first part, the mouse is already at a radius r0. So the mouse still needs to swim a distance 1 minus r0, at least. But if the mouse goes with a certain angle alpha, then it has to swim a distance L, which is longer than 1 minus r0.
But why would the mouse want to swim more than needed?
Because it will also force the cat to run a longer distance.
Oh yeah, indeed. The cat has to run at least half a circle, so a distance pi. If the mouse goes with a certain angle alpha, the cat will have to run a longer distance. This distance will be pi plus theta, where theta is the additional angle that the cat has to run to catch the mouse.
But why will the cat not go in the other direction and run a distance pi minus theta?
But imagine you are the cat and you are opposite to the mouse. You need to run choosing a direction. Then only will the mouse choose its angle so that it goes in the opposite direction of the cat.
But then the cat can change its direction.
Indeed. But the best strategy for the cat is to always minimize the angle between the cat and the mouse. Since the cat goes angularly faster than the mouse in this second part, it will be closer and closer angularly to the mouse as time passes. Therefore, going the opposite direction would only make the distance longer. Let's make a simulation to see it.
We can see on this simulation that at no point the cat has any interest in switching direction. We have drawn the diameter on which the mouse is located to verify this. The intersection of this diameter with the circle marks the only point where the cat enjoys a true choice of direction, as both paths from there to the mouse are symmetric.
Once the cat has chosen a direction, we can see that the cat never crosses that point again, and will therefore never gain anything by changing direction.
Yeah, I am now convinced. The cat should never change its direction. Yet, if the cat is stupid enough to change its direction anyway, let's not forget that the mouse can also do the same. At some point, the cat will once more be opposite to the mouse. At this moment, the mouse will be closer to the edge than where the second part started. So it is the same situation as the initial one, but with the mouse closer to the edge. So clearly, it is not interesting for the cat.
To sum up, choosing to go in a straight line with a certain angle, alpha, might work. Let's see if it's advantageous in practice.
And to do that, let's write the equation to calculate this.
For the mouse to escape, it must reach the edge of the pond before the cat reaches that exit point. Let Tm be the time the mouse needs to reach the exit point, and let Tc be the time the cat needs to reach the exit point. So the mouse escapes if Tm is smaller than Tc.
To calculate those times, we need to know the distance and the speed of both the cat and the mouse. The distance the mouse has to swim is L, and this distance the cat has to run is pi plus theta.
Given that, the mouse reaches the edge in a time L divided by Vm, and the cat reaches the same point in pi plus theta divided by Vc.
This can also be rewritten as L is smaller than r0 times pi plus theta.
To know the best angle alpha the mouse should choose, we now need to express both theta and L in function of alpha. This requires some trigonometry. First, let's begin by expressing L in function of alpha.
To express L, we can apply the generalized Pythagorean theorem on the triangle. This gives the formula that's written on the slides.
From this, we can derive L as shown. We used the fact that L must be a positive distance, so we ignored the negative solution.
Secondly, we need to express theta in function of alpha.
To do this, we can apply the sinus ratio rule in the triangle, which gives the written expression.
And solving it, we get theta in function of alpha.
For the mouse to escape, we had the equation L is smaller than R0 times pi plus theta. Replacing L and theta by their expression in function of alpha, we get the equation in the middle of the slide. As long as the inequality holds true, the mouse escapes.
More than this, the mouse actually wants to choose alpha such that it maximizes how much in advance it will reach the edge before the cat. The advance is the difference between the first side and the second side of the inequality. We call this difference phi. This is the value that should be maximized in function of alpha.
To find alpha that maximizes how much in advance the mouse arrives, we can search for the value at which the derivative of phi in function of alpha is equal to 0.
And after some work, which you can see on the slide, we get an equation that we can solve analytically. Solving this equation, we find that either alpha is equal to pi over 2 or that R0 is equal to 1.
And we can reject that second solution because if R0 is equal to 1, the mouse has already escaped. Indeed, the radius of the pond is equal to 1.
The first solution, alpha is equal to pi over 2, is either the best or the worst angle to choose. The same can be said about alpha is equal to 0, as there is no other extremum in the interval 0, pi over 2.
We know that one of these two is the best solution, so let's compare them in a simulation.
Okay, we have this simulation, and we can see that the competing mice are ready on the starting block. Let's start the race in 3, 2, 1, go!
The cat is choosing a direction. The mice flee as quickly as they can. The distance is narrowing. Will the first mouse escape? Here the cat comes and... Oh no! The first mouse is eaten. But what about the second mouse? Will it survive? Yes! The mouse has escaped!
Yes!
The mouse has
Super cool!
escaped!
And we can see here that the best straight line is the perpendicular one. Therefore, the solution proposed by Numberphile is the worst possible straight line.
Let's now calculate how much better our mouse is compared to the Numberphile's one. For that, we want to calculate the maximum speed ratio between the cat and the mouse for which the mouse can still escape. And this for both strategies.
For the Numberphile solution, the calculation is easy. The distance the mouse swims is 1 minus R0 and its speed v. The cat runs at distance pi at speed vc. Therefore, the maximum speed ratio at which the mouse escapes is pi plus 1, which is roughly equal to 4.14. In their video, Numberphile mentions that the value must be somewhere between 4.1 and 4.2, so our exact value matches what they foretold.
For the best solution, we can recall the equation we previously derived. L over Vm is equal to pi plus theta over Vc. Replacing L and theta by their values and replacing alpha by pi over 2, we obtain, after a little bit of algebra, the equation on the slide. Unfortunately, this equation is non-analytical.
We can, however, use a numerical solver to get an approximate answer.
Yes, and if we do so, we get a ratio of about 4.603.
Yeah, that's 11% better!
Great,
Yay!
11%! But is it really the best we can do? The best solution cannot just be a straight line, can it?
Hey, you at home, what do you think? Should we try to find an even better solution?
Oh, yeah?
Well, it seems at least one person said yes, and it may have been us. Let's go.
Yeah, but it feels like it will be much more difficult. Let's give it a try.
This time, the position of the mouse in the pond in function of time is expressed as a polar coordinate, r, and theta in function of t. The position of the cat can be expressed the same way.
As before, the trajectory of the mouse is defined by the parameter alpha. But this time, this parameter is not a constant and depends on the position of the mouse.
Let's quickly recall the formulas for the angular and radial speed of the cat and the mouse. Let's be careful that this time, the angular and radial speed of the mouse depend on alpha, and therefore also on the time.
The angular distance between the mouse and the cat is called phi, as we can see on the drawing. The mouse will escape from the point if this angular distance is still bigger than 0 when r of t is equal to 1. The goal is to maximize this distance while coming closer to the edge.
To do so, we will need to search for the minimum decrease of phi per increase of r. This can be achieved by computing the derivative of phi in function of r and optimizing it. After replacing phi by its expression, we have a sum of 3 terms. Let's calculate the derivative of each term one by one.
The derivative of a constant is 0. That was easy. The second part is a bit more complex because we don't have the expression of the radius in function of time yet. But we can use trigonometry to find the ratio between dt and dr. We can now use this conversion in the formula to obtain the derivative of the second term.
For the third part, since we don't have theta in function of t, we will need to change the derivation variable. Let's multiply by dt on both sides of the fraction, and with the knowledge from the previous slide, we can now calculate the derivative of this third term.
We have here the sum of the derivatives that we call psi. We will now calculate the extremum of psi in function of alpha. Indeed, alpha is the only thing the mouse can choose over its trajectory. Therefore, we want the mouse to always pick the best alpha in function of r. The solution is written at the end of the slide.
Now that we have the angle alpha, we can find the path taken by the mouse. We need r in function of t, which we can find using the definition of the radial speed. The equation is still a bit complex, but can however be solved analytically with software like Wolfram Alpha. The resulting expression of r in function of t is written at the end of the slide.
After that, we just need to find the angular position of the mouse, which can be found using the definition of the angular speed. And now, we can plot the path of the mouse over time. And finally, reveal the best solution.
It's a straight line.